So just start up today's class. So in the last class we were discussing about analog to digital converter. So in which we have discussed about successive approximation results. So before that we have seen what are the different digital to analog converters have been also been studied. So in which binary weighted DAC, so binary weighted DAC as well as R to 2 DAC was used for converting the digital to analog equivalent. So we have got the output staircase waveform. So in that you can see that is nothing but analog waveform. So for 4-bit binary weighted DAC also we have seen as well as 4-bit 4-bit R to 2R ladder also we have seen. So we have seen some of the advantage which is going to have if you are going to use the R to 2R ladder. So we have seen across that. So and for any number of bits you can use only 2 registers are required. Hence that is going to be an optimal as well as it is going to provide a optimum that is a conversion will be accurate, and hence R to 2R will be selected when compared to the binary weighted, because in the binary weighted so we are not going to have a resistance which is going to be equivalent to that of binary scaling. Value of that of the resistors will be not available in the practical scenario. Hence R to 2R ladder forms best for conversion of digital to analog conversion. And then so we have studied about the successive approximation resistor type of ADC, in which we are going to compare the unknown analog input voltage with a known digital to analog converter output. So we are going to see, so it is 4 main components which are required in this architecture. So one is the comparator. So the comparator is required because it is going to compare the unknown analog input voltage with the analog voltage converted from the 8-bit tag. So this is nothing but digital to analog converter. So that is analog equivalent voltage VA will be compared against input voltage, and if the input voltage is greater than VA, then obviously the output, since it is a comparator, so obviously there will be 2 states. One is a positive saturation as well as negative saturation. So depending upon that, so you can see the non-inverting terminal, if it is greater than this inverting terminal, then obviously it is going to be in the positive saturation, and if the inverting input voltage is greater than non-inverting input, then obviously it will be in a negative saturation. So which will be acting as a control signal, or it is going to act as a signal for which you are going to retain the corresponding bit to 1 or reset the value to 0. So this is how we are going to check for the successive approximation. So at the beginning, so you are going to apply the start signal. So whenever the start signal has been given, so the data, all the bits will be MSB bit will be given with will be set to 1, and remaining from Q6 to Q0 all the bits. This is an 8-bit successive approximation. So we are going to change the value, and continuously we are going to track the analog voltage corresponding equivalent digital conversion. So what we are going to do, so for every clock cycles we are going to check the bit whether if it is going to be 1 or 0 by comparing with the analog digital to analog conversion output. So if the analog input V in, if it is greater than VA, then the corresponding bit I am going to make it as a 1 itself. If the analog voltage VA, that is a 8-bit DAC input voltage, analog voltage is greater than this V in, then that corresponding bit will be reset to 0. So like that we are going to individually set and reset by checking the condition of the comparator. So based upon the comparator output, we are going to make it to as a logic 1 or logic 0, like that. So for every bit we are going to check by giving certain constant input, and then corresponding output we are going to get. So at the for every clock cycle, so we are going to check like this, and with the next clock cycle, so we are going to check the next MSB bit, and then so like that 8 clock cycles are required. So whenever it has been started, so whenever the start signal has been activated, so after an 8 clock signal, after 8 clock cycle, so the conversion complete will be enabled. So whenever this conversion signal is enabled, then only your latch is going to provide the digital output. So till that the 8-bit latch will be continuously as soon as you vary the Q7 to Q0 bit, so the corresponding value will be also be uploaded in the 8-bit latch. But whenever the enable pin is activated, so this enable pin will be activated only when the signal is completed. So whenever it is a conversion signal, so this enables this 8-bit latch, and then at that corresponding point, so all the 8 bits will be available at the at the output of the 8-bit latch. So this gives them corresponding analog signal equivalent digital representation you will be getting over here. So whatever the analog unknown input signal is there, so corresponding digital representation you will be getting as the output over here. So this is about the successive approximation registers. This is nothing but working of that successive approximation register. So with this, I'll just move on to the next topic. So in that we can also design by using monolithic DAC also. So in which to design using an IC, which is going to convert the analog signal into corresponding digital representation. So this is not there in the syllabus. So just how to aware about the working of the successive approximation register. So and this is nothing but a monolithic IC design using ADC. So that is monolithic using successive approximation register ADC. So next we have we'll be moving to the next topic, which is nothing but a small signal half-wave rectifier. So small signal half-wave rectifier, which is a very important topic. So in the half-wave rectifier, so in any of the communication technology, so when you are going to conversion techniques are considered. So whenever you need to convert from analog to digital, so this rectifier plays a major role. So this is the first component which is going to be used in the process of conversion of analog signal to digital signal. So that is nothing but a rectifier. So in this rectifier, so we have already studied also what is there inside. So that is nothing but a basic component which is going to be used in this rectification is nothing but a diode. So diode is a component. So based upon that, whether it is forward bias or reverse bias, so based upon the operating principle of the diode, so we can able to connect the analog signal so to be converted into a corresponding pulsating DC signal. So analog signal AC signal will be given as an input for the diode, and corresponding DC pulsating DC will be getting as an output. So whether it is a half wave or full wave, so based upon that, so we are going to see whether the polarity of the diode. So if the polarity of the diode is forward bias, in that case it is going to allow the signal to pass. If it is reverse bias, it is going to act as a off switch, and it is not going to allow any signal to pass. So that is the functionality of the diode. So that functionality only we are going to use it in the process of rectification. So that is the rectifier. So if the polarity of the diode, which is going to work for both the cases of for both the half cycle, that is a positive half cycle as well as negative half cycle, then that corresponding rectifier is called as a full wave rectifier. The same way, so bridge wave rectifier also it will be there, so which is going to provide efficiency, so good efficiency. So here also we are going to deal how the rectifier or how the diodes can be used in the op-amp, how it can be used to rectifier, because we know that in the conventional rectifier circuits and all, so we can see. So I'm just showing the displaying the signal. So single diode can be used as a rectifier. So for this single diode, so if I'm going to apply single diode with a resistor, so will be considered we can be considered as as a rectifier. For this signal to get activated, so what is that? So you have to apply the signal voltage that should be greater than 0.7. So if the type of the diode which you are going to use, so that depends upon the there is a built-in junction potential. So whenever it is need to be forward bias or reverse bias, the amount of voltage which you are going to apply, so that should be greater than this barrier potential or junction potential. So that junction potential or the barrier potential must be greater than 0.7. So in the case of silicon, so in the case of germanium, so the barrier potential will be just equal to 0.3 or 0.2 respectively. So whenever the input voltage greater than 0.2 will be forward bias. So if the input voltage is less than this junction potential, then it is not going to be allow the signal. So since it is required to bias in forward bias and mode, then only it is going to allow the signal to pass. if the diode is reverse biased, or if the input voltage is less than 0.7, then obviously it is not going to be passing the signal to the output. So that is what the diode concept, right? So now for this diode, it is going to work only for greater than 0.7 volts. Whereas if I am going to employ the operational amplifier with active circuits, if I am going to employ the op amp circuit, so this op amp can able to, so this diode, so with this diode, if I am going to employ in this configuration, in which you can see this the total entire circuit, it is going to function like a voltage follower circuit. So why it is voltage follower circuit? Because the input has been given to the non-inverting terminal, and the output of the diode, that is the final output of the diode, it has been given fed back to the inverting input. So since there is no feedback element, so complete output has been since there is no feedback resistors, the entire complete output has been fed back to the inverting input. So the circuit within a fraction of second, so as soon as you apply the input, so within a fraction of second, so the inverting terminal will be same as that of the non-inverting terminal. That means the output is going to follow the input signal. So what we are going to do in this circuit is, so we are going to place this diode in between the op amp output and the actual circuit output. So this is nothing but the circuit output, and this is nothing but the op amp output. So op amp output, we are going to mention it as a V0 dash, and diode D1, so it is going to be inserted between the op amp output as well as the actual circuit output. So actual circuit output is being given to the inverting terminal. So as soon as you apply the input terminal, so the output voltage is going to follow that of the input signal. So since it is going to have only one diode has been connected over here, so you can see, since whenever the positive output of the op amp is arriving, then only the diode is going to be acting as a, it is going to allow. That means it is going to act as a closed switch only when the output of the op amp is positive. So whenever during the positive half of the cycle, so you can see we have just considered 200 millivolts peak to peak signal as an input sinusoidal signal. So you can observe that is the input is being given as in terms of millivolts, whereas diode, if you are going to use a conventional diode, then the diode is not going to work with respect to millivolt signals. It has to be greater than 0.7 volts. So right, so 0.7 volts, if it is greater, then only you can able to rectify those signals. Whereas in this case, now we are applying the input as 200 millivolts to peak. So 200 millivolts peak to peak means 100 millivolts in positive direction as well as 100 millivolts in the negative direction. So during the positive half cycle, so we will see so how it is going to work the circuit operation. So during the positive half cycle of the input, so the non-inverting input is this. So the output will be obviously the output will be in terms of volts only, because of high gain. So because of high gain, so you will be getting some output voltage. So this output voltage will be usually in terms of volts, because input voltage has been given. So the output voltage will be getting over here. So this followed by the diode D1. So the op amp output will be in terms of volts because of high gain. So no need to think. So since it has been not so at this moment, so since it is not been applied up with the inverting output, so we can see since it has been not given feedback, so at this moment, so we not dash, so the output will be in terms of volts. Since it is in terms of volts, so diode D1 will become followed by. So obviously we know that the amplifier gain is in terms of 2 into 10 power 5. So here you will be getting with respect to positive, you will be getting volt which will be greater than 0.7. So that followed by the diode D1. So whenever the op amp output followed by the diode D1, so you will be getting some output. So the output voltage as soon as connect, so it is going to followed by. So this output is being given to the back to the inverting input. So within fraction of seconds, so within fraction of second in terms of microseconds itself, so the output since it is being given to the inverting input, so in order to equalize this non-inverting as well as inverting, so the output is going to follow the same as that of the input voltage, because it is going to act like a voltage follower circuit. So output is going to follow as that of the non-inverting terminal voltage. So the output is going to follow. So you can see as you increase during the positive cycle, so output is also going to vary with respect to 0 to 100 millivolts only. So here also the output voltage is 0 to 100 millivolts because of a voltage follower configuration. So now what will happen if the input voltage is during the negative half cycle of the input. So during the negative half cycle of the input, so as soon as the input goes during the negative half cycle below the reference line 0, so what will happen? So this output V naught dash, it is going to follow same as this. So since the input to the non-emitting terminal is going in a negative direction, so obviously the output is also going to be in the negative direction. So whenever the op amp output is going to be in negative direction, so this diode D1 will become reverse bias because of the polarity of this diode. So input to the diode D1 V naught dash is going to be in negative direction. So here I have just mentioned the output voltage with respect to this one. So at this end, what is the output voltage you are going to get? So that it has been represented over here. But V naught dash, it will be in the negative direction. So negative direction, and then since the output of the op amp is negative, so this diode D1 will become reverse bias. So reverse bias means it will be what? So it is going to disrupt the feedback path. So it is going to act as a open. So open means what? So from this no voltage will be appearing over here. So that means it is not going to pass any voltage from the op amp output to the circuit output. So since there is a the diode D1 is going to act as an open circuit, so this V naught dash is going to get saturated in negative direction. Why? Because so since it is going to act as an open circuit, so the feedback from the output to the inverting input is going to be gets affected. So feedback will be get affected in the sense there will be no feedback virtually during the negative half cycle. So during the negative half cycle, so the V naught to minus inverting input, so there will be no path has been established, because of which, so since it is connected to the inverting terminal, so the output will be, the circuit output will be remains equal to 0. So since the circuit output will remain equal to 0, so the op amp will get saturated in negative path has been affected. So since the feedback path is affected, so the op amp will get saturated in negative direction. Negative direction means minus it is going to get saturated minus VE. So since the op amp output will be in op amp will be negative saturated, so output will get settled in the 0. So during the positive cycle, you will be getting as that of the same as that of input, because the diode D1 is going to complete the feedback path. So you will be getting voltage follower. So the circuit is going to function as a voltage follower. So the output will be same as that of input. Whereas during the negative half cycle, so since it is reverse bias, so it is going to feedback path. So since it is going to affect the feedback path, so the output is going to be held at 0. So during this time, so op amp will be operating in negative cycle. That means op amp will get saturated in negative direction. So again, whenever the input again comes back to the positive direction during the positive half of the cycle, then only the diode D1 will become forward bias. In this way, so you will be getting, so this is the output. So why I am stressing out this op amp getting saturated is because so whenever the op amp will get saturated, so this is going to affect the performance of this small signal half wave rectifier. So whenever the input signal is going to be operating in negative half cycle, so op amp is going to get saturated in negative direction. So this requires time. So it will be get saturated in negative direction, right? So as soon as the input signal is going to be moving into the positive half cycle, so this when it is going to move into the positive half cycle, so what will happen? So the op amp needs some time in order to come back from the negative saturation. So some time is required. So because of it is going to affect the performance of the system. So it is going to require some time, and the circuit is going to require some time. So in order to come out of this saturation, and hence you can call this type of circuit or this type of rectifier as saturated positive small signal half wave rectifier circuit. So this is the drawback which is going to have see in this case. So now the same thing. So if I'm going to reverse the polarity of the diode, so if I'm going to reverse the polarity of the diode, so instead of positive small signal half, this is the diode D1 is going to be will be connected in the reverse direction. So whenever the input is in the reverse, that is you're going to apply. So the whenever the negative whenever the input signal is going to be whenever the input signal is going to be in the negative half cycle of the input is going to arrive, then only this diode D1 will becomes forward bias. During the positive half cycle of the input, so this diode D1 will be in reverse bias. So negative half cycle it is going to act as a forward bias. So positive half cycle it is going to act as a reverse bias. So in this op amp circuit configuration, so during the positive half cycle of the input, so the op amp output is going to get saturated in positive direction. So when the diode D1 is going to operate in reverse bias condition, so in that case the op amp is going to be saturated in positive direction, because this positive signal is not going to be allowed, and hence the circuit will become functioning like an open loop. So circuit becomes open loop because so you'll be having only the input terminals, that is Vin is going to be applied over here, whereas for this the output will be 0. So 0 will get compared with this input voltage, and hence during the positive cycle, so the op amp output will get saturated in positive direction. So there will be no feedback path in this during the positive half cycle of the input. So feedback path will be not there, means the circuit, the op amp is going to operate as a open loop. So only during the negative half cycle, so circuit is going to, is whenever the diode D1 is going to be acting in forward bias, then only the circuit is going to function like a voltage follow. That means the negative feedback is going to apply. So in that case, the output is going to follow the input. So only during the negative half cycle. So in that case, the circuit is going to get saturated in positive direction. So this is about the negative small signal of a rectifier. So in both the cases, we can see the op amp getting saturated. So in order to overcome this, because the circuit is not going to the circuit, so it is not going to be operated for it is going to increase the operating frequency, and hence so another negative half wave rectifier is to be designed, so such a way that we need to eliminate this saturation region. So negative half wave rectifier is shown in the figure. So another I am going to represent the negative half wave rectifier. So in this case you are going to use the two diodes. So in this case you are going to get the two diodes, so that the op amp output so the op amp output is what? So here it is nothing but V naught dash. So V naught dash is not going to get saturated. So in the previous case we were telling that the V naught dash is going to get saturated, but now by employing these two diodes, so this V naught dash, the op amp output is not going to get into saturation, and hence it is going to minimize the response time. So as I told, so whenever it requires more time is required in order to come out of the saturation, so that means the response time was more when in the previous two cases, and also the operating frequency range was high in the previous case. So now it is going to, when you employ this type of network, so it is going to, the op amp is not going to saturate it, and hence the response time is will be less, and along with that the operating frequencies are going to be less. So let us see the operation of this circuit, so that how we are going to avoid this saturating during the positive half of the cycle. So now for this configuration we are going to have negative. So this is nothing but a negative half wave rectifier. So in this case, why it is called negative? Because so the input has been given to the inverting terminal. So this is the input signal through the this is the input signal source, and through the input resistance R1, it has been fed to the inverting terminal. So any input signal, if it is going on to the inverting terminal, means we know that it is going to be what? So it is going to be inverting terminal means what else means any input signals, if it is connected to the inverting terminal, so the output will be 180-degree out of phase with respect to input signal, and hence during the positive half cycle of the input, so the output will be negative going. So if the input is positive going, then the output is going to be negative going. So negative going means, so you can see this is a positive going, so it is going to be negative going, so V naught dash. So whenever the input to output is negative going, so in this two diode cases, so we can see one diode D1 will be forward bias and D2 will be reverse bias, because since the output of the op amp is going to be in negative direction, so that forward bias the diode D1, whereas that reverse bias the diode D2. So from this output to the inverting input, so this feedback path will be discontinued because this diode D2 will be acting as an open path, so open circuit, so we are not going to have. Whereas during the since the output of this forward bias this diode even because of the negative going input output, so this completes the path in the for the negative direction, so that so during the positive cycle of the input, so you will be getting the output as a so negative direction, so negative direction, so you will be getting the input as this, so the output will be having this as a output, so certain gain will be there. So if I'm going to maintain the gain, that means RF by R1, right? So because it is an inverting amplifier, so you'll be having V naught will be equal to what, minus RF by R1 times of V in. So if I'm going to make the feedback resistance as well as input resistance same, then you'll be getting unity gain. So in that case, so whatever the input is there, so if I'm going to make RF is equal to R1, so the output will be same as that of the input, but the opposite 180 degree out of it. So it is going to pass only the negative half of the cycle into input. So V naught dash followed by this diode even. So now what will happen during the negative half cycle of the input? So during the negative half cycle of the input, so since it is given to the negative half cycle of the input to the inverting terminal, so output of the op amp will be positive going. So since the output is positive going, so you can see the polarity of the diode. So polarity positive going means so this diode E1 is going to be reverse bias. Whereas this since it is positive going, so the diode D2 is going to be forward bias, and this from this the output of the op amp so through diode D2 becomes forward bias, and it is being given to the inverting terminal, and hence as soon as the input is going, so the same output is also going to be in opposite direction, and hence the output at the inverting input it is going to settle in the ground, and the output is going to be n0. So you can see this is the negative going, right? So this is the negative half cycle of the input, so it will be positive, it is going to be positive going. So this positive going will be given over here means, so here it will be positive going and here it will be negative going, so both will get settled in the virtually ground. So the output from the op amp as well as the input of the signal so will get settled in the zero level, and hence it will both will get cancelled, and hence so since there is a deception over here, since we are going to take the output from this condition, so the op amp output, so op amp will not get saturated in any direction. So that means since we have given positive signals, so we will be getting as a V naught dash. So this positive will not get saturated because we have employed the negative feedback. So since we have employed negative feedback, so op amp will not get saturated in the positive direction, and hence the output will get settled in zero. So the only difference between this circuit and the previous two circuit is that we are going to have so the negative saturated, so negatively saturated, so there will be no saturation is going to be seen in this case, so that is going to automate, and the response time is going to increase in both the cases. Since this is the circuit is required because it offers advantage over the previous circuit, so only thing is that we are going to imply two diodes. So by implying these two diodes, we are going to make the op amp not to get saturated in any of the cases. So in any of the cases, you can see from the op amp output, so we are going to imply the feedback path is not affected in both the cases. So during the positive of cycle, so this is going to be completes the feedback path, and you are going to get the output as same as that of the input. So during the negative of cycle, so the output will be positive, and this since it is positive, so this reverse bias and this forward bias. So from this, the op amp output will be completes the feedback path, and hence the output will not get saturated. So this is the advantage of this small signal, negative small signal SAR rectifier. So if you reverse the polarity, the same thing. So instead of a negative small signal going, so you will be getting the positive signal going. So this is if you reverse the polarity of the diode D1 as well as D2 complete. So when you employ this, so you will be getting the output will be positive, output will be getting. So that is what the small signal rectifier. So you can see the output resistance is non-uniform since it depends upon the diode. So in other words, diode D1 is on, the high input the D1 will be off, and by connecting the voltage follower circuit at the output. So this is about the because voltage follower. Why? Because so the feedback resistance is same as that of input resistance. So during the positive cycle of the input, V naught will be negative, and hence forward bias the diode E1 and closes the feedback loop through the RF. So you can see since diode is during the input cycle, so output will be negative going. So that forward bias diode E1 and that completes the output, so feedback path, and hence the output will be negative going during the positive cycle. And then since the feedback resistance is same as that of the input resistance, so the output voltage will be same as that of input. So we'll be getting the output same as that of input. So whereas in the negative alteration of the input, that means the negative signal, negative half wave of the signal. So there is a negative half cycle of the input, so output will be positive going. So the same thing. So the output V naught dash is positive, hence the diode D2 will be forward bias and D1 will be reverse bias, and hence the D2 will be forward bias. So D2 forward bias agate. So this forward bias and it will be connected to the inverting input, and we can see in fact this diode prevents the op amp from going into positive saturation, since feedback path is not disturbed in this case, since we have employed during the both positive as well as negative cycles. So the op amp output is being given to the feedback path, so to the inverting terminal, so the feedback path is not affected, and hence diode will not sorry op amp will not enter into the saturation. That means positive saturation it will not go, and hence the output will get settled at 0 volts. So this is what the circuit operation of the two diodes small signal negative half wave rectifier. And if you reverse the polarity, you can get the positive half wave rectifier. So they may ask you to in the exam, they may ask write the circuit diagram for positive half wave rectifier without saturation anta ಕೇಳಿದ್ರೆ. So you have to write this two diode circuit. So you have to check and you have to write you should get the output positive half wave rectifier. So in that positive half wave rectifier you have to reverse this polarity, then you will be getting positive half wave rectifier without saturating. So if I am getting saturating, whereas if they ask specifically simply the half wave small signal half wave rectifier, means you can write these two circuits. So during the positive as well as negative, so reverse the polarity of the diode. If you reverse, then it will be positive as well as negative half wave rectifier. Whereas if they ask specifically design a circuit for small signal half wave rectifier such that the op amp should not get saturated, means you should have this diodes D1 D2 as well as the resistance and all you should design. So the value of the non-inverting terminal resistance, so that will be equal to the parallel combination of these two. So we know that in order to get the unity gain, so RF will be made equal to R1. So whatever the resistance you are going to keep, so at the input resistance R1, the same thing I should keep it as for the feedback, such a way that the output will be same. So minus RF by R1, so RF by R1 will be giving the unity gain. So whatever the input combination is there, so parallel equivalent, so that if I'm going to have, so that will be going to offset minimizing the resistance. So this is nothing but offset minimizing. Why you are going to get for 4.7K is so 10K into 10K, so that is 100K divided by 20K, so it will be around 5 kilo ohms. So nearly 5 kilo ohms, so you're not going to get a standard 5 kilo ohm resistance, so you're going to get standard resistance as 4.7K. So that I'm going to design over here. So 4.7K. So this resistor is called as offset minimizing. Why? Because so if I am going to provide the equivalent resistance, or the value of the current that is flowing inside the inverting as well as non-inverting terminal, both will be remain same, and hence in order to equalize the bias current, so we are going to use a resistor equivalent to that of these two values. So in that case there will be no offset voltage, and the input signal as well as output signal, if you compare, so it will be exactly same. So that is what offset minimizing resistor is. So in the circuit figure 9.25, so V in is equal to 200 millivolt peak to peak. So that is half wave saturating half wave signal rectifier. So V in is equal to 200 millivolts peak to peak, means 100 millivolts during the positive direction and 100 millivolts during the negative half wave. And the frequency sine wave at a frequency 100 Hz has been given. Draw the operation of the circuit and draw the output waveform. So the same thing here, whatever the signal is, whatever the input waveform is being given. So this is the signal waveform you should draw. So this is a half 200 millivolts sine 200 millivolts sine wave input signal has been given, and this is nothing but a circuit diagram you should draw, and this is the output you should draw for that one, and you have to write the explanation for that. So that is what is happening during the positive cycle of the input. Diode D1 conducts, therefore output follows the input because the circuit is going to function as a voltage follower, and output is going to 100 millivolts peak. During the negative cycle of the input, so diode D1 will be reverse biased, and hence output voltage will be zero. Hence this is the explanation for that. So with that, we have just completed the half-wave rectifiers topic. So next topic which we are going to study is today active filters topic. So in this active filter topic, which we have already studied in the labs. So lab. So what do you mean by filter? So that is filter is nothing but in the terms of communication field. So if I'm going to talk about the filter means, so this filter is going to filter is called as a frequency selective circuit. So that is going to select a certain band of frequency is going to select, and other signal frequency which are of not interest, so it is going to block. So that is nothing but operation of a electric filter. So in this electric filter, so only signal which is going to allow or nothing but your frequency which is of interest, and other frequency band frequencies is going to be attenuated or blocked. So what is this filters and how it has been classified? So filter circuits may be classified into mainly three types. So one is analog filter as well as a digital filter. So since we are going to deal in the electronic circuits, so two type of signals. So analog signals are also be there, and as well as the digital signals are also it will be there. So we are going to have analog as well as some digital filters topic. So if the input signal is analog, then we are going to have analog signal, and if the input signal is going to be having the digital signal, then it is going to hold it as a digital filter. So passive filter as well as active filter. So there is a classification of filters. So passive means if the filters design is going to be done by using only the passive components like resistor, inductor, resistor, capacitor, inductor, and all. So then that type of filter is called as a passive filter. And if it is designed with respect to active components, if it is present in them, so then the type of filters are called as an active filter. So active component like what? So operational amplifier or transistors or any sort of active component if it is there. So along with the passive components, if any active component is also involved, then the type of filters is called as a active filter. Op amp, along with the resistors as well as capacitors, if I'm going to use op amp or if I'm going to use some transistor as an active component, then that type of filter is called as a active filter. So another is the depending upon the frequency range. So if it is going to be operated in the audio frequency range or in the radio frequency range, so we are going to classify that type of filters as audio frequency filters or radio frequency filter. So we are going to see what are the type of classification, and the same thing what I have just discussed. So the same thing we are also having. So analog filters means analog, it is going to deal with analog signals, whereas the digital filters means it is going to have digital signals. It is going to process analog signal using a digital technique. So digital filters means the same thing. So whereas we are going to use the digital technique, so we are going to have analog signal in the digital signal convert ಮಾಡ್ಕೊಂಡು, so then that signals digital signals will be used. So that is nothing but a technique which are going to use in the case of digital filter. So depending upon the elements, so what type of elements, whether it is a passive elements, it is used or active elements, so it is being considered as a passive filters or active filters. So passive filters are nothing, what are the classification, what are the components it is going to use. Resistors, capacitors, and inductors will be used in the form of a design. So in the filter circuit, so that circuit is called as a passive filter. On the other hand, if I am going to use a transistor or an op amp in addition with the resistor and the capacitor, so then that circuit is called as a active filter. And in terms of frequency, operating frequency range, so if RC filter, so we have seen in the oscillator circuit and all. So the RC filter circuit, if I am going to use, so for the audio as well as low frequency range of frequency, so R and C, so both resistor and capacitors are going to be used for filter circuit. So if the R and C components, if it is going to be operating in the audio or low frequency range of operation, then that type of frequency filter is called as audio frequency filter. Whereas if I'm going to operate, by using the feedback element, the L and C component, or if I'm going to use the crystals, if it is going to be used, so then that type of classification you're going to have it as a crystal frequency. So it is nothing but a radio frequency range of operation. So that is going to have a high Q value. So already we have seen in the oscillator. So when I'm going to use a crystal oscillator, you're going to have a high Q factor, and for stable unaffected with respect to environment or a component values. So we are going for crystal oscillators, or crystals are going to be used for stable operation at higher frequency, and hence that type of component, if I'm going to use a high frequency range, then it is called as radio frequency filters. So what is the importance of so in this chapter actually we are going to deal with active filters topics. Okay, so with respect to passive filters and active filters, what are the main differences, and what is the advantage you are going to have over passive filters, we are going to discuss right now. So already we have told, so what do you mean by active and passive filters? So active and passive filters means active means you will be having op amp or transistors will be used as an along with the resistors and capacitors to be in the design of filters, so that is called as active filter. Whereas in the passive filters, only the resistors and capacitors can be used. So in that case, what is the difference between these two, and what is the advantage as well as what are the disadvantage in each of the cases we are going to see. So in audio frequency ranges, inductors are often not used because we are very large and costly. So we are going to not use in the audio frequency range, and hence only for design and analysis purpose, we are going to use in the audio frequency. That means low frequency range of operation. We are going to use this active filters. So what is an active filters, and what are the advantage of passive filters? So as I told, so there are three important points. One is first important is also gain and flexibility, frequency adjustment flexibility. So gain is very important parameter. So flexibility is also another important parameter. So gain means what? So in if you are going to use only razor and capacitor, so you cannot able to increase the gain. So there will be no point of increasing, because passive components will consume the signals, and hence they are going to dissipate in the form of heat. Whereas active signal, if you are going to use, then the component if you are going to use, so you can able to, if I am going to use a op amp as well as a transistor, obviously if I'm going to use a transistor as well as op amp as a circuit in the filter design, then obviously you can able to increase the gain, because by varying the feedback path or resistance, so you can able to increase, or you can able to adjust the frequency. Flexibility will be given for this case in the active filter. So since op amp is capable of providing a gain, so input signal is not attenuated as it is caused in the as it is in the passive filter. So passive filter very resistors and as well as capacitance if it is going to have, then there is no point of increasing the gain. So that means gain andre, so output voltage versus input voltage if you calculate, so if it is greater than the input voltage, then it is called as a gain. So in this passive filter only resistor and capacitor will be there, and there is no point of gain. So output will still will be attenuated. So not it is going to increase, so it is going to still become attenuated. And hence that is a disadvantage in the case of passive filter, when compared to the active filter, because it is going to have a pump in the form of gain. In addition, active filter is easier to tune or adjust, because since you can able to vary the frequency, so frequency of the signal, it is easier to tune or adjust the frequency, and hence this is a very important parameter when compared to passive filter and the active filter is considered. So there is no loading problem. So we are going to, since the op amp is going to be used, or a transistor if I am going to use, so obviously you are going to have input resistance as well as low output resistance. So you will be having a high input resistance as well as low output resistance, and there will be no loading problem. So whenever you need to connect from a high impedance source to low impedance load, so the active filter is not going to cause any load on the source side as well as the load side. At the same time, cost. So cost also plays a major role. So in any topic, so any IC design or any type of electric filters is topic. So cost typically the active filters cost is going to be more economical than that of the passive filters. So why? Because so the op amps as well as because the cheaper rate of the op amps, so we're going to have that advantage. So because of that, these three are the important point which has to be considered in the case of active filter when compared to the passive filter is considered. So with this, I will just conclude today's class. So, in the tomorrow class, I'll just go through all this type of filters. So already you are familiar. So just I'll just do the recap. So what are the low pass filter means, high pass, band pass, band reject, all pass filter, everything I'm just going to discuss. Okay. Thank you.
Thank you, sir.
Any
Thank you,
doubt
sir.
is there? Mm.